What's an exponential function?
Do you want to find out? Okay.
Let's talk about exponential functions. They've been in the news a lot because exponential functions are things that grow really, really fast, right? Let's say I have 5 bacteria and they're doubling every day. So that means after one day, instead of having 5, I have 10. And then after another day, I have 10 times 2, 20. And after that, I have 20 times 2, 40. And double, and double, and double, right? Let's say that Y is my number of bacteria. So if this goes on and on and on, how can I write 5 times 2 times 2 times 2 times 2 times 2 in a shorthand way? I could write it with an exponent. 5 times 2, how many times? Well, x times, right? And if I just made a little XY chart, on day 0, at the beginning of my experiment, that would be 5 times 2 to the 0. If we recall, 2 to the 0, any number other than 0 raised to the 0 is 1. There's my 5. After one day, that's 5 times 2 to the 1. That's 5 times 2, that's 10. After 2 days, that's 5 times 2 squared. Well, that's 5 times 2 times 2, which is 20. On the 3rd day, that's 5 times 2 to the 3rd. That's 5 times 2 times 2 times 2, or 40, and so on. Hey, show me with your body. If I were to graph this, where Y was the number of bacteria, and X was the time in days, what do you think this graph would look like? Show me with your body. That's right, exponential growth. We know what exponential growth looks like. It grows slowly at first and then goes faster and faster and faster. Okay, this is an example of exponential growth. Now, what would that value be right there? Well, that would be my starting value, 5, right? So this is my starting value when my x is 0. In other words, on the 0th day. And this is my, in this case, my number of bacteria. Okay? Very nice. So that's an example of exponential growth. What do you think exponential decay would look like? You got it. That would be exponential decay. So this is exponential growth. Let's look, exponential decay would have a graph where you start at a certain amount, but you're zooming down exponentially. So let's say I'm starting with 100 bacteria. So I'm starting with 100 bacteria. What type of number would I have to multiply 100 by to get something smaller? Is it going to be a number bigger than 1 or a number less than 1? Yeah, it's going to be a number less than 1, between 0 and 1, some fraction. Let's pick a nice easy fraction. Let's say 1/2. Okay, so this could be the graph, which obviously a loose graph, of an exponential, whoops, I wrote growth there. What the heck? This is decay. This is decay. Exponential decay, where I'm multiplying by a number between 0 and 1. And so my 100 is going to get smaller and smaller and smaller. Let's go ahead and plug in some numbers. When x is 0, I have 100 times 1/2 to the 0. 1/2 to the 0 is 1, so 100 times 1 is 100. So that's where I'm starting, at 0, 100. Okay, after one day, well, I'm multiplying by 1/2 to the 1. Well, that's just 100 times 1/2. Well, that's 50. Okay, after day 2, well, that's 100 times 1/2 squared. That's 100 times 1/2 times 1/2. well, that's going to be 25, and so on and so forth. That's exponential decay, all right? But again, the structure of my equation is the same. This is my starting value when x is 0. And this sometimes we call our growth or decay, in this case, ratio. In this case, it's our decay ratio. Okay? And in our exponential growth, right? This was our growth ratio. All right, these exponential functions are so fun and they are so relevant because so many things grow exponentially in our world. Bacteria, unfortunately viruses, any kind of population begins by growing exponentially. All right, let's explore some more of these, shall we?